Hey there, focused learners, and welcome back to The Explainer. Have you ever actually stopped to wonder how the world's biggest apps store and fetch your data so incredibly fast? Every single time you search for a friend, load a profile, or pull up your purchase history, you're relying on this massive, completely hidden architecture. Today, we're cracking open the high-stakes world of database storage to understand the true backbone of the internet, B-trees and B-plus trees.
So here's the mystery we're gonna solve together today. First, the backbone of databases. Then, B-trees versus binary trees. Next, how B-trees actually work, followed by the B-plus tree evolution. And finally, why B-plus trees absolutely dominate. Okay, let's dive into this.
Part 1. The backbone of databases, the where and why. Think about systems like MySQL's InnoDB engine, Postgres in the indexes, SQL Server, Oracle, SQLite, even almost every file system metadata store out there, they all use B-trees or B-plus trees. Basically, almost every major relational database relies heavily on these specific, block-oriented structures just to keep the internet running smoothly. Literally, if you were to just magically erase these data structures from existence right now, global data retrieval would grind to an absolute halt. No way around it.
And get this, here is the most shocking number you're going to see today, 3 to 5. Yep, that's the surprisingly tiny number of levels a B-plus tree actually needs to store literally billions of keys. Just think about that for a second. You could have a billion rows of data, and your database only has to drop down 3 to 5 levels to find exactly what you're looking for. It's wild. But to understand how that massive scale of efficiency is even possible, we really got to look at the alternatives.
Which brings us to Section 2. B-trees versus binary trees, in-memory versus on-disk.
Now, if you've ever taken a computer science class, you're probably pretty familiar with in-memory structures, like red-black or AVL trees. And hey, they're fantastic when all your data fits comfortably right in your RAM. But there's a fatal flaw here. When you move to physical hardware and deal with slow disk I/O, things change. Disks read and write in large, fixed-size blocks. So a standard binary search tree is just way too tall and thin. That means every single time you follow a pointer to a child node, you might be triggering a brand new, painfully slow disk read. Enter the B-tree. It's essentially a multi-way search tree specifically optimized to solve this exact hardware limitation by kind of just flattening the whole tree out.
But it's really not just about spinning disks anymore. Stack Overflow user Radu actually points out that B-trees are faster than any binary search tree due to memory locality, which results in fewer cache misses. Now, what's really interesting about this slide is that even when your data is in memory, the B-tree's design still comes out on top. Because a B-tree packs multiple keys into a single node, modern CPU hardware can just prefetch that data. So you're doing linear searches inside the node, and it is blazing fast.
Moving right along to Section 3. How B-trees actually work, under the hood.
All right, to really understand a B-tree, you kind of have to think in buckets. Instead of one node holding just one key, a B-tree node corresponds directly to a physical disk page on your hardware, typically around 4 to 16 kilobytes in size. And that single block, it's accessed in one single disk read. So by stuffing dozens or even hundreds of keys into this one giant bucket, the database can grab a massive amount of routing data in just one single I/O operation. Of course, to keep those searches efficient, the B-tree has to enforce some pretty strict rules. Like every node has a maximum number of children, let's just call it M, and to prevent the tree from getting all lopsided, every non-leaf node has to be at least half full. Plus, and this is absolutely crucial, all leaf nodes must appear on the exact same level. This right here guarantees the tree stays perfectly balanced and perfectly wide. So what actually happens when one of those disk pages gets completely packed full? Well, when a node hits its absolute maximum capacity, it splits. The median key literally gets pushed up into the parent node, and the remaining keys get split evenly right into two brand new child nodes. Which means something completely counterintuitive when you think about it. Unlike normal binary trees that grow downward by adding leaves at the bottom, B-trees actually grow upward from the root.
Now, for all the technical learners out there tuning in, let me just reassure you with the hard computer science facts. Despite this incredibly wide branching and tight packing of nodes, our core operations, insert, delete, and search, they all remain highly efficient. We're talking O of log n time complexity with an O of 1 space complexity footprint. So you still get that incredible speed of a logarithmic search, but it's perfectly tuned for disk blocks.
All right, Section 4. The B-plus tree evolution, a game-changing tweak.
So here is the fundamental structural difference between the two. In a standard B tree, every single node holds the keys and the actual data. But in the B+ tree, the internal nodes hold only the keys. They act purely as a routing table, like a map. All of the actual data, or the pointers to the data rows, they live exclusively down at the very bottom in the leaf nodes.
Because all that data is pushed right to the bottom, the B+ tree can do something basically magical. It connects all those leaf nodes together sequentially. So the crucial point is this doubly linked list. It allows forward and backward traversal right at the data level. And guys, this is the single secret weapon of the B+ tree that just completely changes everything downstream for database queries.
Which brings us to our final section, Part 5, Why B+ trees Dominate, the Industry Standard.
And this brilliantly illustrates exactly why this works so well. Because we pulled all that bulky data out of the internal routing nodes in a B+ tree, we freed up a massive amount of space on those disk pages. Think about it. A 16 kilobyte page that could maybe only hold 200 keys in a standard B tree. It can now hold 500 keys in a B+ tree. And a higher branching factor means a substantially shorter tree. And a shorter tree, that means way fewer slow disk seeks.
And this translates to massive real-world advantages. Remember that doubly linked list we just talked about? Well, it makes SQL range scans, like when you query a price between 100 and 500, absolutely trivial. You literally just drop down to the leaf and read straight across the linked list. This gives you sequential prefetching cache behavior and allows for much simpler localized concurrency protocols like latch crabbing. Basically meaning multiple threads can safely and efficiently read and write to your database at the exact same time without locking the whole thing up.
So B+ trees are clearly the undisputed champions of on-disk ordered key workloads. But as we look to the future of cloud-scale distributed systems, where write-heavy workloads are kind of the new norm, it leaves us with a really provocative question. If B+ trees conquer the spinning disk, what structure is going to conquer the cloud? Will log-structured merge trees or LSM trees take the throne? Well, we'll save that mystery for our next explainer. Keep learning and stay focused.